Hello, and welcome to Module 4. We're going to be starting talking about Chapter 3 in probability. Probability is going to be odd, and I'm going to do something, again, I don't like to do too often. This is me. Hello. Is talk, because I have to talk a little bit without much that I'm going to write. We have learned how to observe things through our data. We've put measurements to variables. I'm sorry, I have a camera that's in the one, and so we can measure things. The thing we want to know is, what do those measurements tell us about the truth? A lot of statistics is trying to find the truth, or what the real value of something is. When we say it's the science of observation, we are looking, we're measuring, and now we want to know what that measurement means within our variable of interest. The problem is, the truth is not cut and dry. And so what I want to talk about before we really dig into why we're going into probability here is some old philosophies of what reality is. I don't want to approach the matrix idea of it. Is what is really real, and how we have to then take that into account when we go to observe things. And I'll build this up. So this first little bit here is kind of an introduction into Chapter 3 probability, and then we'll deal with the mathematical rigor of probability fully. So in doing probability, the first thing that we want to really say is that if statistics is the science of observation, what are we observing? And in the most fundamental way, we'll call that reality. Not even how you spell reality. I don't even really know if reality is reality. Reality, yeah. Versus realty, which is selling houses. Spelling is not my strong point. And so philosophers have thought about this for ages, and we even have little children's songs for it. And in mathematics, we'll develop what are called maths use axiomic systems. Axiomic systems. And we found in mathematics that eventually you reach a point where you can't prove anything anymore. And so you have to state things that are true. And the axioms in general is, you'll state, I'm building a number system, the unit will be 1, addition is defined, that if I take 1 plus 1 I get 2. These things have a counting principle based off of tick marks, but we have to define them. And we define the unit 1 as having meaning. 1 isn't an inherent thing. And then we define what addition is. And these things might have parallels to reality, but we assume that they always work. And there are some assumptions that go into axiomic systems. I think in geometry, this is Euclid's geometry, worked very well, where the axioms were points and lines, and the definitions of points and lines, and we built all geometry from it. Well, philosophers in the Greek times stood that back, and the Greeks believed very strongly that there were two worlds. There was the world in your mind and the world that was real, or the world outside of the mind. And in a way, they idealized the world of the mind. They wanted perfect circles, and they saw, in the mind, the perfect circle. In the world outside of the mind, lots of ellipses. Right? And this was better, they said. They had this idealized version of it. But coming out of all of that, there came the idea is, how do you know there is something outside of the mind? And from a science standpoint, we don't. There's no way to prove that anything exists beyond the thought you're having right now. You can't prove that there's something beyond your thought. Every piece of reality you get passes through the thought you have right now. That ended up with Descartes in the 1600s with his famous "I think, therefore I am." And Descartes was doing this as kind of a proof of the existence of God. And this was his basic axiom was the only thing you can prove that's real is the thought that you have at the moment. And then through some other arguments, he went through that thought as a copy of something else. Copies are less perfect than the original, and so if you work your way back to the original, the perfect thought would be God. That was Descartes' ruling. But this was the axiom he has. And for most people, philosophically, this is about all you can prove. Without axioms. And so the axioms that we tend to take for granted, the improvable things that we assume to be true, is there is a reality outside of the mind. There's something that exists outside of the thought. This permeates culture as an idea. We even have songs about it. Row, row, row your boat gently down the stream. Merrily, 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 life is but a dream. The Matrix movies, I think, reintroduced this idea to Western culture, where people were all of a sudden like, wait, we could be living inside a Matrix. And people struggle with the idea because we never really go back to the assumptions we make. Or we come to the idea of what if our assumptions are wrong. And so science in general says there's a reality outside of the mind. It is observable. And this is where statistics come in. Right? That means we can measure things. That the things we think we see correspond to things that exist. So we can measure. And then in science we'll go, it follows natural laws. And those laws are the same everywhere. And so when we're talking about statistics, what we're doing is we're measuring to find some truth about reality. And one of the, I guess, it gets more and more common in modern times, and our culture has observed it, is the things we've chosen to measure determine what we see. In physics, that's quantum mechanics. The Schrodinger's problem, right? You have a box. Put a cat in a box. I don't know why I put it with a bottle of poison. That's my drawing of a cat. Should have just done a stick figure cat. Let's do a stick figure cat. Give it justice. Put a cat in a box. Put a bottle of poison. And stick figure cat. There we go. And the cat is both dead and alive until you open the box. Until you observe something, reality exists in multiple states. And this idea of observation underlines our key basics of how we observe the world and what the world means. But we also decide what we observe. Einstein's theory of relativity has the faster something moves, the slower the clocks move with it relative to something standing still. And what we found out was we measure distance was the thing we were measuring, and we also measure time as the thing we are measuring. Draw an old clock here, right? These are the two things we're measuring. But the true reality, once we look at it closer, is these two things are linked in something called space-time. And we're just now learning what that means, because when we start making things go really fast, we see this linkage. And so reality itself is only going to expose what we look at it. And this falls into what we do with statistics. Now, luckily, a lot of the statistics we're going to do are very easy to measure things. But what we have to realize is by observing, we have chosen the variable of interest. We're only going to see certain things. Now, another thing comes about from this is that underlying all of how we measure things, and I'm going to use a ruler as my example. If I want to measure this, and this is as good as my ruler is, well, inches, centimeters, it doesn't matter, right? Millimeters. Well, I know when I go to record this measurement, it's at least 4 whatever, and then I can look here and go, well, it's about 4.5. And if I go to measure again, I'll draw it a different color to measure again. And I get, well, that's closer to 4. So I've taken these two measurements of the same thing, and they're not quite the same. And I tried to show that it sticked a little bit past the side here. And what we call this is error in measurement. And it's not a bad error. It's just by the nature of measuring, our measuring devices will never be perfectly precise. I could zoom in, and every time I zoom in, I still have this problem of having a gap in my scales, right? I said this could be inches or centimeters. This could be nanometers. This could be, I could make this smaller and smaller and smaller and smaller, and yet I would still have a gap between the units on my marker, and where I line up the end, if it falls in between it, I have to guess or estimate, and that creates an error in measurement. It means I'm not measuring the true value, the reality that we're trying to get to. But error in measurements, if I measure really, really good, if I have good clinical procedure, then the error in measurements are random. Now, do you see why this is? I'm turning it where the probability comes from. Is that, and I'll give a summation here shortly. But so error in measurement should be random. And so when I go to measure a thing, if I take many measurements, then maybe the true value, and I'll put true, is best estimated by the mean of all those measurements. Oh, and since this is a sample space, I'll use a sample mean. Right, is our best estimate of truth. Notice it's not the truth. It's the best estimate of the truth. And we're going to start moving towards that language where we're going to be estimating the truth. Well, there's another horrible secret in all of this. In the reality that we now know physically, let's say I had an ultra accurate, I'm using a laser. And so each one of these markers is a complete wavelength of light. And so I can measure down to 570 nanometers, right? That's like a red laser. 390s. Yeah, we'll do 390. In the 300s is like a red laser. And so I'm measuring individual wavelengths of light. But even the thing I'm measuring is made up of atoms. And atoms are vibrating. They're constantly in motion. The only time atoms don't move is if we could get them to 0 Kelvin. And we've never gotten anything to 0 Kelvin. In fact, that's what the Kelvin temperature scale means, is when you get to 0 Kelvin, the atoms will no longer be moving. And so the thing I'm actually moving has different lengths based off of when I look at it. It will have expanded, it will have contracted, it's bouncing up and down like a spring. And if you ever watch a spring bounce up and down, sometimes it's longer, sometimes it's smaller. And so this truth of length has what does it mean when it's bouncing? And so that's another randomness. And the actual motion of particles when heated is done completely by a thing called statistical mechanics. Notice the name. Or we also know it as thermodynamics. And it deals with randomness in motion. And so one of the things that underpin our universe is random events. A particle could bounce this way, could bounce this way, right? It could go up in energy or it could give off energy. The causal relationship for it comes down to probabilities. Now, this happens for everything we observe. So on a very primal level, and the reason I'm going to primal physics on it is whenever I bring up probabilities to someone says, well, you could figure out, right? You could figure out, and I'll use the thing we'll be using a lot of here, which are dice, right? That's my horrible cube drawing, right? I throw a die, and if I knew which end was facing up, and I knew how hard I threw it, and I knew how it hit the surface, I could predict which side was coming up. But all those parameters to know and to measure precisely with all the random error measurements means that throwing a die is a truly random thing, if the die is constructed in a way to be fair. And so in a lot of things we observe, the true thing that we're seeing is affected by a lot of random parameters that we can or cannot measure. And so understanding randomness is going to be our link between descriptive statistics and inferential statistics, because we need to know how chance affects the truth we see. And as you'll see, good data reporting should not say, and I'll go back to the length of the ruler. So let's say my variable is x. I'm going to say the length of that ruler was 4.5 centimeters. And I say that with certainty. Well, that's not good data. Good data would be saying that's 4.5 plus or minus 0.25. Let me do this properly. Plus or minus 0. Let's see, the type of estimate I did, so 0.450, 25. And this is a way of stating a range of values. Or we could say it's 4.50 with a, well, I'll get to that more. Good data reporting includes a range of values or a likelihood, how likely a value is, or a certainty. And we'll find methods for doing this. But all of these reportings require us to understand how the plethora of random events that are happening affect what we observe. And so people always wonder, well, you're getting data and you're going in through, now I want to go to infer, and all the course takes this detour into probability. Some courses start right off with probability, but it isn't a detour. It is the link between observing something and making inference from it. We have to take into account random. And so that's what we're going to do in chapter 3 and 4 and 5. We're going to look at random distributions. And so if things happen randomly, what do they look like? So that we can then compare it to the things we've observed.